Hello, everybody. Yeah, thanks, Hugo, for the presentation. As you said, I'm going to talk today about latency and reliability in LEO, small satellite communications. And I'm the lucky one that got the last slot of the last day of this intense week. So the challenge for me is to keep your attention, actually. But I hope you will like this topic. So the outline.
It involves space, so I think we will stay awake. It's very
okay. So the outline I have for today is the first part will be to introduce about these LEO small satellite constellations, because maybe not everybody is familiar with this new technology, and there are some interesting aspects of these new networks. And then I will go a bit more into technical topics, and I will talk to you a little bit about the inter-satellite link and how the resource allocation is challenging in this link. And then the last part, a little bit about end-to-end performance, latency and age of information, and then a little bit about routing in LEO constellations. Yes, so there is right now a lot of hype about satellite constellations, and one of the reasons is this technology of small satellites. The first CubeSat was launched in early 2000, but it's probably now in the last years that they are reaching a level of maturity in which it makes sense to think of competing with terrestrial networks or complementing terrestrial networks in some use cases, some applications. So the thing about these small satellites is that they are very good for the market because they are small and they are cheap. The smallest units you can have is the CubeSat, the one that you have in the picture. This is only 10 by 10 by 10 centimeters, and it's less than 1 kilo. And then you can pile several of them if you need some more advanced features, because of course in 1 kilogram it's a bit limited what you can do. If you need more, you can use several of these units, but still keep the price quite low. The fact that they are cheap is one reason, is that they use commercial components. And the second one, very important, is because the weight is very low. And because of this, they can launch it as secondary payloads. You have to think that in the total cost of a special mission, the launching is a very important part of it. It can be even half of the total price. So if you reduce the price in the launching, then you are really reducing the price of the total mission. And another interesting feature is that the development times are short. So in 1-2 years, maybe you go from the requirements and the design to the satellite that is flying and up and running. And this means that your technology will not be obsolete very fast, like it happens with traditional big satellites, where the development times can be several years. So for all these reasons, there is like a lot of market excitement, and also now 3GPP is very excited about satellites, and they want to integrate them in 5G. The other aspect is that these small satellites, they will typically be flying in low orbit. So this is also different from the traditional space missions, which were with the big satellites flying at geostationary orbits. The geo orbits, they are at 36 kilometers, and you always see the same satellite. So you always have the same connection, because they move at the same pace as we are moving with the Earth rotation. But now, if we use lower and lower orbits, it means that we are, for example, for LEO, we are talking about between 500 and 1500 kilometers. It means that the same satellite is not visible all the time for us, but what happens is that we have a satellite pass which lasts few minutes. So from horizon to horizon, I will see one satellite for a few minutes. This, for the communication networks, it means a lot of new challenges. The infrastructure, my base station, which is the satellite, is moving. Actually, it's moving very fast. If I want to keep continuous coverage, I need to have a lot of these satellites all connected to each other. And actually, if you want to have like global and continuous coverage, then you will need, the number here is above 40, but usually it's probably a bit more if you also want some overlapping and some reliability on your coverage. So we are talking about hundreds of satellites as the usual size of a constellation. And then because you are changing the satellite that is serving you, covers all the time. So it's a challenging communication network. The big advantage of going to low orbits is the latency, because one of the limitations of traditional satellite communications is the latency, because you have the propagation delay that you cannot do anything about it. That's physics. We cannot optimize anything there. So for GEO, the propagation delay is already more than 100 milliseconds. So of course, this is really far away from the 1 millisecond that Cheda was mentioning this morning for URLLC. If we go to low orbits, then we talk about a few milliseconds. For example, at 1,000 kilometers, we have 3 milliseconds. So if we want to do anything that is close to low latency, it has to be LEO. Yeah, so we combine these two things, the small satellite technology and the LEO, and we have these LEO small satellite constellations. As I said, usually you will deploy hundreds of these small satellites, and 3GPP has decided to integrate them in 5G or post 5G, because it will be in the next releases. So it's not the initial release of 5G new radio, but it will be the next ones will include these LEO constellations. Actually, it's part of something bigger, which is called in 3GPP non-terrestrial networks, NTN. And it includes drones, it includes balloons, and it includes satellites. And in satellites, they have LEO, MEO, and GEO orbits. So they have everything in this category. I don't have much in the presentation about the details of 3GPP, but one interesting thing to mention maybe is that it was decided last December to continue the work not only on 5G new radio, but also to start a separated study for narrowband IoT. So to see which are the modifications to the protocol in narrowband IoT to be able to have your base station in one of these satellites. Yeah, and here in the picture I have, well, how one of these constellations looks like. So you have, in this case, these polar orbits, and we have these hundreds of satellites that they are organized in orbital planes, and they work all together as a single communication network. And you will have, I mean, you have the CubeSat structure or similar to this. And you will deploy antennas for the different links. You have a link to the Earth, to the user equipment on Earth, or the ground stations or gateways, any device that is deployed on Earth. And then you will have one of the axes goes with the velocity, so with the movement of the orbital plane. There, what you will typically deploy is antennas to do the intraplane intersatellite connection. So in your orbital plane, you will be talking to the satellite in front and the satellite behind you. That's the typical implementation. And then on the other axis, you can deploy antennas to talk to satellites that are in other orbital planes. So if you look at my pointer, so this would be like in the intraplane, so talking to the satellite in front and behind. And then I can also deploy connections to satellites that are in neighboring orbital planes. The intersatellite link, the ISL, is not always deployed. That's true. The mission because it's expensive to do it. But for these missions like Starlink, these big ones that are coming, that they have the ambition of being global internet provision and very general purpose missions, these ones they have to implement it because if you have to guarantee any latency and any end-to-end performance, then you need to deploy it. But it's true that there are other simpler missions that they just have the traditional link to ground, and that's it. Then you have to wait until the satellite reaches the destination. Okay, in terms of applications, there are different uses of satellite. The classical application is for remote areas because satellite constellations, they are ubiquitous. So you can cover areas that it's too difficult with a terrestrial connection or it's too expensive. And they are also used to complement the terrestrial networks or to complement big satellites. If we talk about IoT applications in particular, there is also a lot of different use cases for satellites. I did here a classification depending on where are the things, because you can have the classical case where your devices are on ground. So, for example, in the context of 5G, so the massive MTC, where you have a lot of sensors deployed and you have to read them, in this case from a satellite. And if it's a massive connection, the KPI would be, the main challenge would be this having a massive amount of data being collected. But we have other cases with satellite. For example, we have some interesting applications on the air. When you have airplanes or also drones, you have this technology, ADS-B, which is for tracking airplanes. The idea is that the airplane is all the time reporting status information regarding the position, the velocity, the direction, and so on. So it's to create awareness, so everybody knows where the others are. And this in the ocean has to be supported by satellite. Here, the KPIs can change and the challenges are different. Here, you might be interested more on the reliability, the latency, or the age of information. I will talk about this in a few slides. Your things can also be in the oceans with satellites. You have also very strong technologies here, this AIS and the new VDES, which is replacing AIS. This is also for tracking, but it's for tracking vessels. And you could also have 5G is looking at some, 3GPP is looking at some cases with wind farms, offshore wind farms in this case. And finally, you also have applications which are in the deep space. If you want to look at some astronomical events or you want to have some space communications, here the challenge is typically the latency. So this is to say that besides the use cases that 3GPP defines and is looking at, there are other technologies that are related to satellite and are relying on this technology. So it's very heterogeneous what we find here. In the case of IoT, I also highlight here the differences and the challenges compared to terrestrial IoT. As I mentioned, here you have the infrastructure which is moving because your satellites are moving. And because of that, your contact times are short for some of the links. And we have a Doppler effect, which has to be compensated. We also have, in general, higher propagation delays than terrestrial IoT, so this has to be considered in the protocol design. And because we are using small satellite technologies in many cases, not in all constellations, but the ones that I have been looking at, there are constraints. There are constraints in the infrastructure power, in the size, and in the processing. The last one, the processing constraints, can also represent a challenge if you want to implement any kind of machine learning in very limited and cheap satellite. This is a classification of the physical links, but I already mentioned more or less these two links, the ground-to-satellite link and the inter-satellite link. The ground-to-satellite link, it's important to mention that it can be to the UEs or to the final device or some gateway that is collecting information from several devices. But we also mean here the link to a ground station for the constellation management or for other purposes. And this is also known as the feeder link in space communication books. But we group them in the category of ground-to-satellite link. And then for the inter-satellite link, I mentioned, it can be intraplane, in the same orbital plane, or interplane. And here we have some numbers for the performance that we can achieve in the constellation. We are plotting cases where N is the number of satellites per orbital plane and P is the number of orbital planes. So we play with these two numbers. So it also changes the total number of satellites in the constellation. And we have here on the left the propagation delay, which is for a constellation, as I said, around 1,000 kilometers would be something like 3 milliseconds. So this is for the GSL, and you can also see for the ISL how it changes depending on the parameters that you set, but we are always in the few milliseconds up to 10 milliseconds. For the Doppler shift, we don't have the issue of the Doppler in the intraplane ISL, and this is because the relative distances are preserved because everybody in the orbital plane, they are moving at the same time. But in the other links, it's challenging. So it's one of the main problems to be fixed in communications with LEO satellites. And on the right, you have the rates per physical link. So you have what can be reached for GSL in the downlink and the uplink, and for the two ISL links on the median and on the 95 percentile.
Excuse me, just a question.
Yes.
Usually on terrestrial communication, and as you show here, the Doppler shift is only a frequency shift. Would you also see contraction and elongation of the symbol duration?
Yeah.
Would that be an issue at these speeds, or is it still too small?
I think you can have both time and frequency offsets, and even if you compensate, because you compensate on Earth, but still you always have some time and frequency offsets. So yeah.
Javier, maybe I can comment on this. There's something curious about the speed of light, that it doesn't matter what is the speed of the observer, you will always observe the speed of light.
Yes, and I was more thinking there's one known case in interplanetary communications where you had so high relative speeds that you lost synchronization because the time duration of symbols are no longer the same. And in terrestrial speeds, we don't have to care about that. But I was curious if something that you would see in these constellations. it's similar if you do an underwater communication, that the contraction or elongation of symbol durations will lose you to miss-synchronization unless you track it. So but it's a detailed question, so let's not derail it. Thanks.
Yeah. Thanks. Yeah, moving a little bit on the working 3GPP, Cheda, he mentioned this morning about this document where they have the requirements for the 3 use cases, for the 3 connectivity types, URLLC, massive, and EMBB. So if we take the text of the reliability, there is nothing specific yet about satellite. So still the 10 to the -5 with a user plane latency of 1 millisecond seems to be the only one that is mentioned. There is also the V2X, but it's not applicable here. So of course, if we keep the 1 millisecond, there is no way we can do this with satellite. That's it, because the propagation delay is already higher than this. But if we look then at the user plane latency and the control plane latency definitions, they have added something now for non-terrestrial. So for the user plane latency, where there is clause now to indicate that for the user plane RTT, if one of the links is a LEO satellite system, I mean, if you are using a LEO satellite system, then it has been redefined to be up to 50 milliseconds. And for control plane, the same. So it's up to 50 milliseconds. So if this is the case and they decide to redefine the URLLC, then it will be possible to talk about URLLC. But right now, there is not explicitly written there. As Cheda said this morning, this is anyway something that changes from release to release, and maybe now when the work on non-terrestrial networks gets more mature, maybe they will redefine here. But so far, that's what we have. The next thing I wanted to say is that also this working with the latency, it's not always, or with the packet delay, sorry, it's not always the best metric for some applications and some of the satellite applications. So latency has been historically characterized with the packet delay, but in the context of IoT, we have more and more applications like tracking, where you are sending status updates, or applications with a sense, compute, actuate cycle in industrial environments, for example, that are not really sensitive to the packet delay, but it's more to the freshness or to the relevance of the information at the receiver. So if you are sending an update of your position, I don't care so much about the specific packet delay of the latest status update, but I'm more interested in keeping a good track of your position. So how updated is my information about your position? So for these kind of applications in the last years, there is a lot of interest in defining more the performance in terms of age of information and some byproducts from this definition, because they are considered to capture a bit better this value of the information. And yeah, one example for satellite would be when you want to track airplanes. I don't know if you know this website, Flight 24.
Flightway,
yeah. So where you can see real time the position of all airplanes on the globe. In this case, as I was saying, if I'm tracking your position, it's more about does my yellow point really represent the current position, yes or not, rather than if a packet had a delay of 50 or 60 milliseconds. So this is why we are looking in the last years a lot on this age of information. I will show you some results at the end, but the idea is that the age is defined. I'm not going into the details of this slide, but if we look at the figure, it grows linearly. Oh, I cannot. Sorry, it's a bit slow. It's a process that grows linearly when I don't receive anything, and then in the instant when I receive a new packet, I update the age, and now the new value will be the time elapsed since this packet that has just arrived was generated. That's the concept. So it keeps an idea of the age of the current information. Okay, so all this introduction, apart from telling you a little bit about these networks, was to say that I don't want to talk about satellite URLLC actually, because URLLC for many people is the 1 millisecond in 3GPP. And there is not a clear agreement yet that if you have some other cases, I mean, that it's not always 1 millisecond. And if you want to use a satellite, it cannot be 1 millisecond. So I'd rather talk about high reliability and low latency to be sure that it's not misinterpreted. Or in some cases, as I said, age sensitive. Age of information metrics or similar metrics are better for some of the applications that we are talking about. I didn't check the time when I started, so how are we with the timing?
I think you're fairly good. I think the target ending time is 1 o'clock, so it's 20 minutes, but
okay.
Everyone else have been drawn long, so.
Okay. Yes, so next I want to talk a little bit about the resource allocation in the inter-satellite link, because here there are some interesting technical problems. In the intraplane ISL, as I said, the relative distances are preserved, so it's a bit more classical link and it's easier to implement. But if we want to talk to satellites on the other orbital planes, then it gets actually a bit tricky. We can model the constellation like a graph, and the research question would be which interplane satellites to connect to when several of them are reachable. And once I decide who is going to talk to whom, which resources should I assign to each of them? So it's a double problem. It's a matching plus resource allocation problem. And remember that these links in the interplane, it's similar to the ones to ground. They last sometimes for a few minutes. So it's something that you have to dynamically change. In this figure, you can see what's the problem that we are addressing. So we have initially this graph with feasible satellite pairs, and here different colors refer to different orbital planes. So the black ones belong to the same orbital plane. The intraplane is not plotted here because we are only dealing with the interplane ISL. The first step will be to decide who's talking to whom. So this would be like this black line, thick black line on the step 1. So we get a new set of the matching M. And then the step 2 would be to decide, okay, for these pairs that I have decided, which resources are they going to use? And for example, here, the green resource will be used by the pair between 1 and 3, but also by 4 and 6. And the idea here is to include the interference. So I ensure that when I reuse the same, and if 2 pairs are using the same resource, they are not interfering too much to each other, because hopefully they are far away or they don't have so much cross interference. So the result of this process is to have the connection, so the pairs plus the resources. Technically, I just want to mention in the problem formulation, well, we have to define the path loss, and to decide that two pairs, they can talk to each other, we have also a maximum distance, meaning that if they are too far away, we don't really include them in the graph. And the threshold to decide when to stop is the intraplane distance. So we keep as the maximum the intraplane distance. And then we have the matching problem and the resource allocation. In the matching problem, we work with the S and R, so we don't have the interference because we still don't know which pairs we are going to pair. And then once we have it in the resource allocation, we work with the interference. So we have the S, I, and R. But the details are, of course, not important here. The results of this study, where we are talking about a centralized solution, I'm going to talk about it in next slide. For the matching results, in terms of the pairs that are established, we get more or less the same amount of pairs for the three solutions that we investigated. So we have these two solutions, Gridin and Markovian, in this work, and then they are compared to this benchmark, which is a geographical matching from the literature. And in this figure, what I have is the mean sum of rates, and we can see that the Greedy is the one that is getting the best performance in this case. And once we have the matching, for the resource allocation, we have this proposal of a greedy resource allocation, and we can see that it gets much better results than the other two reference solutions, which are using a round robin allocation or a random allocation. And here we are plotting the mean sum of rates versus the number of available orthogonal resources. And we can see that the gain is very high already with a small number of resources. Yeah, so even if we have only two resources, we can see a significant gain when we use the greedy solution with OFDM.
Excuse me.
Right, but yeah.
Just from my understanding, when you say geographical matching, would that be that you're using the location above the planet as a partition of your resources?
Yeah.
Or
Yeah. Yes.
Thanks.
Okay, what's the issue of this solution? That it's centralized. So it's like a fundamental study to understand what's the best we can do, but the problem is that, oh, sorry, I jump one slide. The problem is that we are assuming that there is a centralized entity calculating the matching and the resources every T seconds. We are not including the buffers and the activation in this solution. And the next step would be to look at a distributed solution where each satellite has to decide the channel to be used, and ideally communicating as little as possible, because having feedback and so on in this kind of very dynamic links is challenging. So one solution that has been investigated in wireless mesh networks is using learning automatas. So the idea is that not only the probability of the selected action is affected, but all actions are affected. And this seems to work well in highly stochastic environments. And as I said, it has been tested in wireless mesh networks. Wireless mesh networks have some similarities with constellations. The only thing is that in constellations, things are moving, but you can predict how they move. So this is a big difference that should be somehow incorporated in our solutions. So the next step would be to look more into a self-managed solution, as I said, if possible, without communication among satellites, where the action is assigning the channel and the state is the current channel assignment. And each satellite should maintain like a vector with the probabilities of each channel that reflects the interference history. And when the channel quality is not above a threshold, then a new channel is selected randomly based on this vector. As I said, in a LEO constellation, it would be important to exploit the predictability of the movement. The activity is unpredictable. This is the challenging part. And collecting feedback is, in many cases, not feasible, at least not for each of the actions. So maybe a solution where you collect for a batch of consecutive actions would be a bit better, a bit easier to implement. Yes, that was for the inter-satellite link. Then I wanted to talk a little bit about the end-to-end performance, where we want to see the latency performance from ground to the final destination. And we model this with a queuing network, where we have, first of all, we have a GSL collision model here, because here we assume that we have a random access, big number of devices competing for the channel. And we are using parameters similar to narrowband IoT that we have slightly adapted to satellite constellations, but the protocol is taken from narrowband IoT. So it's in line to what 3GPP is planning to do in the next months. And then once we have this in the GSL in the first node, then we have a number of satellites that are used as a relay, because we are assuming that the final destination is far away. So you need several of these hops to reach your final destination. And we want to see what's the end-to-end performance and what's the impact of this number of relays. So if we have less or more relays. Yes, I can skip the rest because I'm getting a bit late. Yeah, we look at two performance metrics here. First is the total delay or the system delay. This is the classical metric for queuing networks. And it is just scale, assuming that all satellites are equal in these results that I will present. So it's just scaled by the number of hops that you have, so the number of nodes. And then we will also see results of the average age, with and without errors. So we will also see a little bit the trade-off with the reliability. So since we are talking about applications that are sensitive to the age, when there is an error, there is no retransmission whatsoever, because you are assuming that it's just a status update, and if you lose one of these packets, you just wait for the next one, which will be more updated. So when we talk about ISL errors, it's modeled like here in this queuing network. So it's this epsilon that is telling you the probability that your packet will be successfully transmitted or it will be lost. And when it's lost, there is no further action. Okay, yeah, and yeah, I'm skipping the math, of course. I just want to show the trade-offs in the results. So here is the first set of results without errors in the ISL. And we are looking at the impact of the random access in the GSL in the first node. If you look first of all at the solid line without random access, for the system delay, what we have is that when rho increases, rho is the total load, the packet delay will increase. In our simulations, the service time for each satellite is equal to 1. This means that rho, the system utilization, is equal to lambda, to the arrival rate. because usually it's lambda divided by mu, but mu is 1 in these simulations, okay? So if I talk about the load or the arrival rate, it's the same for these results. Okay, so system delay will increase with rho. And then we also observe that when we increase the number of nodes, the system delay will also increase. So the number of relays in my multi-hop network. And the H, it usually behaves with this U shape. This is because the H is different from the packet delay. When rho is very low, it means the arrival rate is very low. It means that I don't have very frequent status updates, so the H grows. On the other extreme, when rho increases, it means that my queues are more and more congested. And because of this, the H at the receiver also increases. So the H is typically minimized in the medium regions. So not too low lambda, not too high lambda. So on the left, the problem is infrequent packet generation. On the right, the problem is congested queues. And then we can also see the behavior with the random access. So we are plotting 3 cases with no random access, is the solid line I was talking about. And then we have 2 cases where the maximum number of attempts is changing. One case is with 1 and the other case is with 10. So 10 means that I can try up to 10 times if there is a collision in my random access opportunity. And we can see the impact both for the system delay and for the average. And we can see how with 10 attempts, it really impacts and the performance, the latency performance gets much worse. The other interesting thing to look at was with the errors. Here we can see on the left, again, the system time, and on the right is the age. And we have different values of the epsilon, which is the average error rate at each satellite. And what it's interesting is if you look at the age on the right, that, for example, when you increase epsilon a lot, like 10% is a very high number, but is to show which are the trade-offs here. What we observe is that for low values of rho, the H is best without errors. But we are working on the congested part, so when the queues are long, it's actually better if you start losing some packets, because it will reduce a little bit the load, and then the H actually gets lower values than when epsilon is equal to 0 or with small values of epsilon. So this crossing effect here is because you have this multi-hop. It's more observable when you have more hops. And it's because, yeah, at some point the question is it better that you just miss some of these packets and then you have the queues a bit less congested. So this is the effect that we observe here. And I'm going to skip this because I'm running a little bit late. Yeah, but in our model here, we are looking at a fixed picture where we have an origin and a destination with a number of hops. But to complete this end-to-end performance study, the next step would be to look at the global constellation and at the routing, no? And which are the routing algorithms that we can use. So how to find the best route for each packet. And if we want to implement any kind of reliable and quality of service aware routing in a LEO constellation, that's really complex because we have this topology that is dynamic and it changes very, very fast. We have this frequent link handover. We have this imbalance load. We have some satellites that are flying over very crowded areas and some satellites that will be flying over totally, over remote areas with almost no traffic. So it's a very complex problem, the problem of routing, but it's the next thing to address, to have a full study of the end-to-end performance. And I took a couple of papers from the literature. There is not much that is specific about routing in LEO that uses machine learning. So there is some traditional paper, using not machine learning, so there is quite a lot of literature, but I didn't find much using machine learning. There is for wireless mesh networks and for managed, there is some literature, but I took two examples that are specific for satellite. The first one deals separately with the problem of the traffic prediction, which is the first thing, because it's really uneven. And they are using this extreme learning machine to enhance the training speed for the traffic prediction. And then they have these mobile agents that are distributed. They have this forward agent going from the origin to the destination. And then once, so it has to find all the routes. So for it, it finds the next hop, and then it will be moved to the next hop and find the next hop, and so on until destination. And then once this reaches the destination, they have this other backward mobile agent that will do the route in the opposite direction. You don't need to calculate it because you know it already. And it refines basically the decisions. So this is the first example of using machine learning for routing, and they show in the paper that they get better link utilization than with an ant colony optimization. And the second example, they use these two hops, state-aware deep reinforcement learning. And it's a simple concept. In the figure you can see, it just means that I will just consider two hops from me to do the decision. And they have some hello strategy to check if the links are available or not. So hello means that they will send hello messages, and then if they don't receive an ACK, then they consider that the link is not available. Yeah, and I'm not going into the details because it's very late. But yes, they have this deep reinforcement learning with some rewards depending on the orbital parameters and the rest of information. Yeah, and they show actually in this paper that they can perform much better than the previous paper, which could be this ELMDR. So the brown one, they perform much better both in delay and drop rate. That's what they show. Yeah, but as I said, this is just two examples, but there is much more to be done in the routing part, and I think that machine learning can help there. Yeah, so I finished now. So in this talk, I wanted to introduce you a little bit about these LEO satellite networks, which are the challenges, how reliability, low latency, and age of information can be supported here. So a little bit on the interplane ISL matching and resource allocation problem, and then on the end-to-end latency performance. And I mentioned very briefly, without much detail, where machine learning can be useful. So in the resource assignment for sure, and this is one of the things that we want to do next, and also in the traffic prediction and on the routing. But there are other open problems, and maybe you have also, after this talk, maybe you have also some other ideas. For the constellation management, I think this will play an important role. So everything related to self-healing and telemetry and management of the constellation, it's too complicated right now because you have this connection to the ground stations that last for a few minutes, and it's too many things you have to do in these few minutes. So moving towards more autonomous satellites. That's going to be very important to have these networks running. And also in distributed processing, there can be maybe federated learning can play a role here. And with this, I finished my presentation. Thank you.
Thank you so much. Do we have any questions for the speakers?
Too bad being the last one.
Yeah, exactly. And I already posed a couple of questions along the line, along your presentation, but you mentioned now the routing problem and the use of machine learning. Do you see that there's a difference in the routing problem for satellite constellations, or is it similar also for mobile and ad hoc networks, for instance, when it comes to the machine learning part of it?
I think the main difference is how this predictability can be exploited. So it's not that things are periodic. It depends on the constellation. Some constellations, if all the planes are at the same altitude, then there is a periodicity, and you can exploit this cyclostationary process on your algorithm. But if they are not periodic, it's still predictable. So you know where things will be next in next time slot. So how this is exploited in the machine learning algorithms, I think that's the main thing that can make a difference.
Thank you, Beatriz, for an interesting talk.
Thank you.